Okay, thanks a lot, Alex. And thank you all for joining us this morning. My name is Steve O'Malley. I'm an energy consultant with Efficiency Vermont, and I work in the multifamily and large commercial new construction markets. And then this is my side hustle doing code trainings because I'm an absolute geek for this stuff, and I need to know it for my job as well. So um, I'd like to just put in a quick shameless plug for Efficiency Vermont in that we have, something there, that we have uh, a commercial new construction program. So offering technical advice, experience, etc., for your designs, and then also financial incentives to help pay for some of the energy efficiency improvements that are above code. So keep that in mind. Okay, a couple things that I have to say here that I'm obligated to say is that material contained in this presentation is proprietary to and copyrighted by ICC. We have obtained and reproduced this information with their permission, and the acronym ICC and the ICC logo are trademarks and service marks of ICC. So first off, we want to get out there, target effective date right around the corner, July 1st. And I think the thing that I want to make sure that I'm highlighting here is that the CBES target effective date, if you have your building permit application submitted before July 1st, then you can design to the 2020 CBES, provided that you complete construction or provided that you start construction prior to December 31st of 2024. And there I have that information right there. Okay, so why are we going to be talking today about thermal shell? Well, in the big picture, we have these code cycle changes every 3 or sometimes 4 years, based on the state schedule, and it's really in support of what we're looking at here. That the state of Vermont has some aggressive greenhouse gas emission reductions planned for the state of Vermont, and if we look at this graph here, we can see that that orange wedge in there represents thermal energy. So that's our buildings. So you can see that's the second largest chunk of greenhouse gas emissions in the state of Vermont after transportation. And so any work that can be done towards removing and reducing greenhouse gas emissions in our buildings is going to help greatly towards the state goals of reducing greenhouse gas emissions. And if you can see, if you look out to 2030, it's saying that the Global Warming Solutions Act, which is the state of Vermont's plan, is saying that by 2030, we want to be 40% below 1990 levels of greenhouse gas emissions. And so if we start thinking about how code plays into this, well, here we are, we've got a code cycle change that we're going through now, and we've got what, 2 more, including the one that would be in 2030. So the code cycle is in part what is helping going to be reducing the greenhouse gas emissions from our thermal sector. Okay, so let's just hop in. So I also want to just highlight that. So today we're going to be talking about the thermal shell sections that are relevant in the 2024 CBES, but also going to be scattering in stuff around building science and building durability, and have some discussions around those aspects as we're having our conversation this morning. So for information on construction documents, what you see in green was what was written in the 2020 CBES. What you're seeing in red are some new language. So it's now saying that air barrier, including the location of the air barrier, has to be included on the construction diagram and construction drawings, excuse me. And this makes great sense. I think about builders who maybe aren't as well versed in building science and focusing on air leakage reduction. By including those elements in your drawing, so that you're including not only where is the air barrier, but what are the materials and the sequencing of the application of the materials to achieve the continuous air barrier, it can't but help the builder in the field when they're trying to execute the plan. A little bit of note about the CB certificate and affidavit. So here we are. We're looking here at the 2020 CB's certificate. And actually, while we're here, one thing I want to point out to you, if you look at the language at the very top in the light gray box, it says, this certificate is for projects whose state or local permit application was submitted on or after September 1st, 2020. The new one obviously will refer to July 1st, 2024, but I want you to know is this is the only place any of this language resides in the code. You won't find it in the actual code book itself. It actually lives on the certificate in terms of which code you have to use. Anything else I want to say here? No, so I guess what I want to get into is that there are going to be some changes to the certificate. So we'll go step through that because a lot of them pertain to the thermal shell. So it's going to require kind of similar to the RB's certificate, more information about thermal envelope details. Air leakage testing, I believe that was required in 2020 as well, but then also an indication of the solar ready zone and other requirements. So here's a section from the new CB certificate. Again, throwing out their draft because this hasn't been released yet. But here we can see that we're going to be called upon to call out the thermal envelope details in terms of the framing or otherwise the overall construction type, and then R values, U values, solar heat gain coefficient, projection factors. So there's a lot of information here that is now going to be required that wasn't previously. And another small section here out of the CB certificate is, if we look under other requirements there, the highlighted section, we've got the solar ready zone requirement, including net roof area after subtractions and the solar ready area itself. And the other thing I'm going to point out to you is if you look up at the very top line of this, you'll see under the air sealing, blower door test, if required, test date. And then the first box you see there is CFM 75 per square foot. And then to the right of that, you see for R2 buildings less than 7 stories, CFM 50 per square foot. And we'll chat a little bit about that later, but just be aware that multifamily buildings are tested to 50 Pascal. All other commercial buildings are tested to 75 Pascal. Okay, so some of the highlights of the changes to code in the building envelope requirements section is that all U value requirements have been adjusted. There is now better alignment with RBs for R2 occupancy classifications. This is, we ought to be saluting the code writers for this kind of effort. Shouldn't really matter if you have a 3-story or 4-story building. They should be designed to the same standards, in my humble opinion. And then an indication of solar ready zone and some other requirements from C4 2.5. And another thing that I really like that they've done with the new code is this example assemblies for meeting the U factor requirement. And I'll touch on that when we get to this next slide. So here we go. We're looking at some of the new requirements for thermal shell for the 2024. I'll step us through the table here real quickly. If we look at the green column, that's what the U factor was for the 2020 CBs. And then in the second column over, the first one in blue, it says all other occupancy classifications. So that's all commercial buildings other than group R2. And we have those U factors. And then we get to that third column, R2 occupancy classifications. And then there we go. So it's calling out multifamily buildings separately. And you can see on this page, there are only 2 requirements that are different from the ones for the overall commercial buildings. So for the attic and other, and for the wood framed and other assemblies, those values are different, but those now follow what's in RBs. So again, that we are designing our buildings similarly. And I want to say that I should back up when I was talking about better alignment with RBs for group R2, our multifamily buildings. Notice I didn't say perfect alignment. It's not perfect, but it's a lot better than it was previously. The other thing I want to highlight that's going to show up in the new code is emphasizing the fact that what you have to design to is a U factor. So when we look, for instance, at that all other occupancy classifications, we have U factors for all of those assemblies. Then when we get over to the two columns on the far right in white, it says example assemblies meeting U factor requirement. And this is a big distinction only in that in the previous code, those two columns existed, but the columns in white didn't call out that it was an example. So many people were led to believe that that was the assembly they had to build to meet code. Whereas the real requirement is the U factor. You as the designer can build whatever assembly you want as long as you're hitting the U factor. But the sections in white are just giving some helpful, hey, here's an example of what that looks like. And a few things to point out on this page. So if we look down here on the right-hand corner on this thing that I'm highlighting, so we're looking at wood framed walls and we're looking at for commercial buildings, not group R2. You'll see the example assemblies are R13 plus R16 continuous or R19 plus R12 continuous or R25 continuous. So from a building science standpoint, everything in there is rock solid. The general understanding for our climate zone here in Vermont is that if we have a minimum of R12 to the outside of our wood sheathing, that we can maintain condensing temperatures within the stud cavity such that the backside of the sheathing will not reach condensing temperatures. And that's great because previous code cycles haven't really brought in I'll call it the building durability side of things here and the building science side of things here. And then anything else I want to say there? I don't think so. But what I do want to point out is part of now over here, if we look at assemblies that will meet the requirement for an R2 and which will also meet requirements similar to RB's, it's calling out an example of you could build an R19 cavity plus an R8 continuous assembly and meet code, but is it a smart thing to do from a building science perspective? The building science says no. So let's not, what the takeaway here is don't be looking at code all the time and thinking that code is smart enough to be taking into consideration building science for all considerations on all assemblies. And so this is an example of where we would advise customers, because our role is in the big picture to be arming people with information, just to say, hey, you could build this assembly, but maybe a smarter assembly is to add the extra R4 continuous to the outside, get to that R12, and then you can sleep well at night knowing you're not going to have issues. Now, that being said, I have seen plenty of buildings constructed previously with R19 or R21 in the cavity and R6 or R9 on the outside, and people are taking smart steps. If you're going to start thinking about reducing that amount of continuous insulation to the exterior, they're doing things like using smart vapor barriers on the interior to mitigate moisture getting in and out of those wall cavities. Okay, second page here in that table for building envelope requirements. A couple things here I want to point out is, so while back here we talked about, yes, the design to the U factor, and there are some example assemblies on the right. When we get on this page, that still holds true. You still have to design to the U factor, or as you'll notice here, the C factor or the F factor. But I just want to point out that the C factor and F factor, unless you've got something like WFI modeling at hand, you're not going to be able to just sort of come up with a simple assembly value, because the modeling involves things like moisture content of soil and soil type and things like that. So the math gets more complex. I think ASHRAE might have some tables in their books that would provide some tables based on insulation thicknesses and giving various C factors. So that would be a way of, if you wanted to design something different than, say, that below grade wall, something different than an R20 continuous, hopefully the ASHRAE tables might have your situation covered, because it's not as simple as just taking 1 over the C value to get the number. And similarly, those F factors that you see under unheated slabs and heated slabs. Two things that I want to point out here, excuse me, on this page. One is again, let's salute the code writers. If anyone remembers unheated slabs in the 2020 CBES, the requirement was R10 continuous beneath the entire slab, regardless of the size of the slab. You could have had a 150,000 square foot building, and you would have been required to put continuous insulation under the whole thing. But we know from an energy loss standpoint, that insulation that's at the very core of that isn't really doing a heck of a lot. So the requirement has gone back to doing 4 feet of insulation, either horizontally or vertically, along the frost wall or just in at the edges of the slab. The requirement is now R20 compared to R10, but at least, again, it seems more grounded in some energy loss science. So again, that's a great one. Another thing that I want to point out that's a change. The other ones don't strike me as necessarily big changes, but these are the ones I want to point out. So here we go, joist framing metal floors. And so now we're talking about floors that are situated above unconditioned spaces. The previous requirement, the U factor equated to essentially R38 insulation. And if I think about this assembly, one assembly that I would see often on large multifamily buildings is it's our parking garage. So you've got a parking garage with steel framing, and then there's a concrete pour deck above it. And if you're looking up in the garage, there was a 650 grid with sheetrock, and then people would just lay in R38 insulation, or sometimes even more, but fiberglass insulation. But now to hit the new U factor, R38 isn't going to do it alone. So you'll notice that there is an example assembly of R38 plus R6 continuous. So somebody is going to have to spend some time thinking about what that's going to look like. Meaning, can you get to that same U factor by adding just more in sort of the big open cavity? Can you achieve it by, is there enough space underneath your large steel framing members to have continuous under there? Or is it going to be something like using gypsum board adhered to polyiso so that you've got an R6 board at the bottom, but you still have a surface to tape and mud from the underside? I don't know. So I'm looking forward to hearing from the design community what those solutions are going to look like. Semi-conditioned spaces now have their own table. So again, 2020 CBES, you can see that all the U factors have increased a little bit. This all used to reside in the previous tables that we saw, but since the addition of the group R2 columns, semi-conditioned spaces now have their own section. Tapered above deck insulation based on thickness. This is again a good change in code. So here we're talking about if we had a flat roof and on one end of the roof we had R20 and the other end of the roof we had R40, we would all look at each other and say, it's an R30 roof. And we'd be wrong. The actual math doesn't really work out that way. It's not a linear relationship. But in terms of the effectiveness of code and people just being able to implement code, rather than do some wonky math to try to figure out what is that real actual number, let's just make it easy and say, let's just take the simple average, because whether that real value was R29.3 or 29.7 or R30.3, it doesn't really matter at that point. But so let's make this easy for people to interpret and to use in their designs. And so now we're saying if you've got tapered roof insulation above the deck, just take the simple average and there you go. And just make sure that the simple average comes out to be R45 continuous for insulation above the deck. While we're hanging out here on above deck roof insulation, again, another building science thing I want to talk about is construction costs, as everybody knows, are extravagant, shall we say, compared to even say 2 or 3 years ago. And so people are looking for ways to trim costs. And one of the questions I frequently get is, can I put some of the insulation on the underside of the roof and then have some above? And so the answer is yes, you can. But if we want to think about good, better, best, the best in class roof that you're going to have when you're putting insulation above a deck is to put it all above the deck. And that way, 2 things happen. One is you can see the underside of your roof deck. So if there is ever a leak, you can easily identify, or more, I should say, if there's a leak and you have a wood sheathed deck, it has the opportunity to dry out, which I think is invaluable. So if you then decide, okay, well, because of budget reasons, we're not going to put everything above the deck. We're going to split it. We're going to put some above the deck, some below. Just make sure to follow what's essentially a 50-50 rule. You want 50%, a minimum of 50% of the R value wants to be to the outside of the roof sheathing, and 50% or less of the overall R value to the underside of the roof. And then the next question comes up, well, what should we use for an insulation on the underside? And I would tell you, you want something vapor closed. But here's where it gets dicier with the building science, because now you can picture we've got essentially a vapor closed insulation above the roof sheathing, and now we've installed the vapor closed insulation below that roof sheathing. So we've created a vapor sandwich, which isn't going to be a problem at all if water never gets in there. The only issue is if water gets in there, there's no good way for it to dry out. All right, I think I'll move on from there. More good things that came in terms of simplifying language around roof assemblies. So there was different language in the previous code about tapered roof insulation versus low-pitched roofs with continuous insulation. And so the 2024 CBES cleans this up by just saying, you know what, whatever type of roof you have with continuous insulation above it, as long as you've got a minimum of R12 at the lowest point, whether it's gutter edge, a roof drain, or a scupper, as long as you're still meeting the overall U factor or the R value requirement for the whole roof. So again, cleaned up the language. I think it's great. Floors. So floor framing cavity insulation or structural slab insulation shall be installed to maintain permanent contact with the underside of the subfloor decking or structural slabs. So that's the language that's in there now. And there are two exceptions. Here's exception 1. Reads, floor framing cavity insulation or structural slab insulation shall be permitted to be in contact with the top side of sheathing or continuous insulation installed on the bottom side of floor assemblies where combined with insulation that meets or exceeds the minimum U values and extends from the bottom to the top of all perimeter floor framing or floor assembly members. So what that looks like, let's get here. Here's an example of what that looks like to me. So here's an example where we have a parking garage within, could be commercial space or multifamily space above it. And if we look at the blue insulation, so here we go. I don't know, trying to think where to direct people's attention. So we can see that there's a slab, and then we can see there's some insulation underneath it. And here's that first exception. So what I see here is what they're talking about. So rather than having to have the insulation up against the underside of that slab, you're allowed to do this if that insulation that is essentially on top of the sheetrock, which is suspended probably by a 650 grid, that needs to meet that R38 sort of, we'll call it cavity plus R6 continuous requirement. And then at the edge, we have to consider that a mass wall above grade, and the code requirement is R25 continuous. So that's going to be a difference here, is that vertical piece needs to meet the requirements of the above grade wall requirement. So in the past, we've typically seen that just be a flash coat of spray foam, just 2 inches, and we've walked away and called it good. And so going forward, that's going to have to meet that R25 requirement based on the way the code reads. And then exception 2, I'm still not really 100% sure what they mean by this. And I would love anybody who has a keener eye to give me an example and maybe sketch out a diagram for what exception 2 is really getting at. So I'm not going to spend time here. You've had a chance to read it here. I will be sending the slide deck around after this presentation. So we've got all your emails. I'll be sending out slide decks in a PDF. Also, any questions that are asked in chat that are live that I'm unable to provide an adequate answer to, I'll do some research and provide those answers back to the group as well. Okay, windows. A couple things here that are, new. So again, I've just thrown in here in green the 2020 CBES values, and then in blue the 2024 CBES. Just so you can see for comparative sake that in general the U factors have gotten a little more stringent. But there are a couple of things I want to highlight. One is that you'll notice that now the second row down, storefront fenestration. We never used to have a storefront category. And the storefront category essentially effectively ended up falling under fixed windows, but they're really different animals, storefront systems and just a fixed plate of glass. So I like the fact that they called out storefront separately, and then they've actually defined what a storefront system is as well, so that if somebody's trying to determine whether or not it's just fixed glazing or is it truly storefront, there is that language in there. The other thing that they've put in here, again, trying to just make things easier and more consistent between RBs and CBs, is row 3. You'll see operable fenestration, R2 occupancy classifications. And again, that did not exist in 2020, but for 2023, you'll see the value, which is interesting. That value is now 0.3. So the U factor used to be 0.28 for residential windows and RBs, and that increased to 0.3. And I'm not sure why. That might just to tie in with Energy Star windows for our zone climate, or maybe it has something to do with trade-offs in terms of when they were doing modeling for cost effectiveness on the RB side, that they needed to back off the windows a little bit to get something in like heat recovery ventilation or something. I don't know the answer to that. I just know that that value increased a little bit. Anything else interesting in there? I think we'll move on. Excuse me. Air barrier performance testing. Old requirement was 0.3 CFM 75 per square foot of exterior surface area, looking at 6 sides of the building. I don't have my bullets in the right order. An exception to that value is R2 buildings. Occupancies of 6 stories or less are going to be tested at 50 Pascal, which follows RBs. And the other piece of this is that the requirement for multifamily buildings is 0.15 CFM 50 per square foot of exterior surface area. So a couple things to note here is, even if we converted the 0.25 Pascal result to 50 Pascals, the multifamily building requirement is still more stringent. You're going to be required to have a tighter building on the multifamily side. And I think that's an acknowledgement of, we've seen that industry consistently build tight buildings over the years and are getting better and better. It seems like every year in terms of churning out high performing buildings on the air leakage reduction side. The other thing I want to point out, you may be asking, well, why do we have 2 different testing standards? And I actually support this and applaud it. It's as opposed to the commercial side of buildings, when we look at our multifamily stock, we have 20 plus years of blower door data and experience testing multifamily buildings, predominantly because of, in the older days anyway, at least Efficiency Vermont's incentive structure and incentive programs. And so that we've got this entire community of architects, engineers, owners, operators, engineering consultants, et cetera, who are so well versed in talking about buildings in terms of leakiness relative to a 50 Pascal pressure differential. And so we can look at each other and say, yo, that's a 0.15 building or a 0.21 building, and people know what that means. And if all of a sudden we were to just have to test multifamily buildings to 75 Pascal, all of that common knowledge and language is lost. And so there's been an acknowledgement in code that, yeah, let's just keep testing multifamilies at 50 Pascal. You'll notice the last bullet here that if you got a large building greater than 250,000 square feet, that is not Group R or Group I, you have the option of blower door testing or doing commissioning. But this commissioning, I don't want you to confuse with building envelope commissioning. This is just a commissioning agent that would be hired to essentially fill out a checklist. And the checklist is found in the CBES document, and it's somebody that have to be out there doing inspections to just look at things like the air barrier and what materials are used. So you have that option of, I'll call that CBES commissioning. because we'll talk about building envelope commissioning agents in a second here, and I want to highlight the differences. Another exception is if it's deemed unfeasible to test. And that has to be determined by the Department of Public Service. You can't just unilaterally decide, hey, my building can't be tested. You have to put it, something in writing and run it up the flag there to the Department of Public Service. An example could be maybe you're building an addition to a hospital and there are no doors between the addition and the old section. It's just all one wide open hallway. And so, maybe at that point you realize, okay, it would be really impossible to test and get a number that's telling you anything. So that could be an example. So what kind of things are we seeing people do to reduce air leakage and hit these metrics? Let me back up. So here we go. Zip system. We're really familiar with seeing that. The things that I want to highlight on this building are that critical details are that you can't see it here because there's a parapet up there at this point, but what they've done is you've got the zip sheathing on the exterior of the building, and where it hits the roof sheathing, the zip system is connecting to that with tape. So you've got a complete seal at the perimeter at the top of the wall before that parapet went on. And the other thing this building has, I wish I had some pictures, is that all of the roof sheathing joints are taped. So you could picture this building's going to get R40, because it's the older code, R40 or R44, I can't remember, continuous insulation on top. And then you'd get your roofing membrane. Well, that roofing membrane is not an air barrier. The manufacturer of that roofing membrane explicitly says our product is not an air barrier. So to define the air barrier and create it where it's actually going to do something for you, it needs to be created at the roof sheathing. And so they've done that here at this building. The other thing I want to just point out that I think is interesting is while this is a zip sheath building, you don't see zip tape on it. I've heard from a handful of builders that they've found better success using a product like a Sega tape, even though they say the warranty goes away on the zip side, that they feel better about the installation and the quality of how the tape is going on. So here's another example. Somebody just used OSB sheathing and then taped sheathing joints. So again, that's how this is one of the main factors in terms of being able to reduce air leakage in the buildings, is getting it at the sheathing level. So if we've now taped our sheathing joints, we've done a great job of reducing air leakage across that, and we're going to have insulation in our cavities, and we're going to have some continuous insulation to the outside of that. But one of the weak spots with this type of an assembly is where we have built up framing members. And particularly you can picture if there is a sheathing joint, a wall sheathing joint in front of this picture that I just put up there. If there's a wall sheathing joint that's taped, there is nothing between the indoor warm moist air and being able to reach the backside of that sheathing tape. And so when we think about, again, moisture management and keeping moisture at our walls and thinking about controlling our condensing surfaces, I've seen a number of builders do this, caulk the backside of the built up framing members so that you are going to reduce the potential for warm moist air to migrate through there. And this is another example of reducing air leakage through sheathing joints that I really like. It's these peel and stick membranes. This one's Harvey Blueskin, but there are others as well. This is a great way of, again, you're getting your weather barrier and your air leakage all in one there. A couple more details. So if we think about at the bottom of the wall when it's tying back into the concrete, if you look at the left there, that's a Sega tape that is being used to go from the zip back across the exposed insulated part of the zip panel and then tying it right back into the concrete. So again, excellent detail. There's a lot of ways this can be done. You can use it with like fluid applied membrane, etc., but this is one way of doing it. And the one on the right you see there is a parking garage detail. That could be a stairwell, or it could be otherwise some other space that is somehow tied into the conditioned space of the building. We find a lot of air leakage at the very top where you see the fluted deck above. Oftentimes people are just either counting on the fire retardant material or wedging some mineral wool or fiberglass up in there to try and calling it a day in terms of reducing air leakage. But really something like spray foam needs to be used if fire safety folks allow it in the design, to be able to really truly air seal up against those fluted decks, because that's a large contributor to air leakage in these buildings as well. Okay, dwelling and sleeping unit enclosure testing. So we had this in the 2020 CBES, where we also known as compartmentalization testing. And the old metric was 0.35 CFM per square foot, tested at 50 Pascal. And so before we were talking about blower door testing the whole building at all 6 sides, now we're talking about blower door testing individual dwelling units or sleeping units. So again, this could be things like assisted living facilities, hotels, barracks, hostels. So it's not just apartments. So keep that in mind when you're designing your buildings. This is a very aggressive number to hit, and this isn't something that I think people are just going to be able to hit willy-nilly. And so between that there's a blower door metric that needs to be hit to demonstrate compliance with CBES. So you're going to have to pay someone to come out and do some blower door testing. And if you have this type of a building, in addition to that, if you have this type of building with dwelling or sleeping units, you're going to have pay someone to do compartmentalization testing. And this is a very aggressive target that's going to really need some thought and detail in terms of how you're going to go about compartmentalizing these units. So from our standpoint, we encourage people to hire building commissioning agents that will be there as part of the design team. They'll be there, kickoff meetings to talk with contractors about the approach. They'll be able to provide progress testing so that you can identify potential issues before you get too far down the road. They can provide the compliance testing for the dwelling and sleeping unit enclosure testing requirement, and then also the whole building blower door. So there's an awful lot of benefit to hiring a building commissioning agent these days with the way the code is. And Efficiency Vermont recognizes that, and Efficiency Vermont has incentives available to help pay for a portion of the cost of that. So please be aware of that. Excuse me. Okay, so compartmentalization testing, fewer than 8 units, test them all. If you have more than 8 units, you need to do 20% of them at a minimum of 7. So real quickly, just wanted to look at what does this sort of mean in terms of compartmentalization. So if here we're looking at an apartment or a sleeping unit from the side, where you see those lighter blue arrows, that's one of the major leakage pathways between, say, the corridor and into the dwelling unit. So we've got to look at this unit in terms of all corners, but that seems to be a major one that we're finding air migrating, particularly depending on the construction type. So the question you've got to ask yourself is, where are we going to define our air barrier? And this is our recommendation, is to identify it at the floor level and at the floor ceiling level, as you can see here, drawn in red. And so these are the types of drawings that we're talking about in terms of trying to help contractors, et cetera, in the field understand where the air barrier needs to be, what materials need to be used, et cetera. And other critical points. Well, I'll just get into some photos here. So here's an example. In this building, they elected to tape the floor sheathing joints to reduce air leakage between floors. Here's using a putty pack on the back of junction boxes. Here is a party wall between dwelling units or sleeping units where the bottom plate is cocked to the floor, and where there are essentially 2 panels, you could think of it coming together, where the OSB, where there was a joint all the way through between the 2 dwelling units, caulking those units as well. And then when we're looking from above, those corners are critical to air sealing. And again, it's a detail that's not typical for construction when we're not thinking about compartmentalization. So get building commissioning agents involved in your projects, get efficiency Vermont involved in projects, and work these things out as much as you can before you get into the field and start construction. Okay, so a couple more things on, let's do this. Let's talk about renewable and load management requirements and additional efficiency credit requirements as they pertain to the thermal shell. So in the previous code, we did have the additional energy credit requirement. That's nothing new. And so for buildings that are greater than 1,000 square feet, you have to comply with that. For buildings that are greater than 2,500 square feet, you have to comply with both the additional energy credit requirement and the additional renewable and load management credits. So that second part there is what is new for code. And we'll hop into that in here a little bit. And so here we go, additional energy efficiency credits. Similar to the previous code, there's a table here based on occupancy group, and it tells you how many energy credits you need. One thing you should notice when you're looking at this is like, there's holy cow, there's a lot more points that are required than there were previously. You know, here we are, the fewest needed by any occupancy group is 30, the most is 90. And I think if we were to go back to the 2020 CBES, maybe the most in a category would be 9. So yes, the number of points has drastically increased, but the points per measure has increased, and there's also a lot more measures to choose from. So one question that comes up a lot is, what about mixed occupancy? And so you want to calculate a weighted average based on occupancy group and to determine the number of points that you need for your building. So here are all the measures that are available to you for obtaining additional energy efficiency credits. So you could think of the way the code works is there's, I'll call it the prescriptive section, when we look at the tables for all the U values and R values, and we look at the mechanical equipment efficiencies, et cetera. So that part of code has to be met. Then there's also this piece of code that has to be met, which is these energy credits. And it can be broken into, there's envelope, there's heating and cooling, service water heating, lighting. Those are the big categories here. So today we're just going to chat about the ones that are relative to our building envelope. So the first is envelope performance. And this is the number of points that you can achieve is determined by an equation that is found in, again, this is all in code. This is for folks that are using 90.1 modeling method for determining or demonstrating code compliance. I don't see this very often, but just want to let people know that that's there. The second one is total UA envelope reduction. So this is saying that the U value of the entire thermal envelope needs to be 15% better than C402.13, which are those prescriptive tables that we were looking at earlier. And you can see the number of points. So, pick your building type that you're working on now, and you can start looking at the number of points that you can get. Reduced air leakage. Tested air leakage has to be less than 0.15 CFM 75. I know my next bullet down there says does not differentiate between CFM 50 or CFM 75, but that's what I'm assuming they're saying there, that it's a CFM 75. And I'd also like to point out here, when we talk about envelope leak reduction, that's still a very achievable number with some thought. And air leakage reduction, so not only does it get you a bunch of points, it's also the most cost-effective thing you can do with your money on the energy front. So in terms of bang for your buck, money spent and then money saved, air leakage reduction is top of the pile by a landslide. So any effort, any money you can spend on that in the early part of your process and in your project design, et cetera, and incorporate some concepts into the field is going to pay dividends for building durability and energy costs and comfort and all those good things. Adding roof insulation. So for a flat roof, if you add R10, on top. I think the requirement was R45, so it'd be saying add another additional R10. Some of these points you'll notice that they can be prorated. So for instance, if you installed R5 continuous over your roof, you would get half of the points. I would also like to point out from where I sit that R45 continuous is a pretty robust roof. And I would say, unless you had deep pockets, I probably wouldn't suggest this measure. R10, adding an additional R10 over the entire roof adds a lot of cost. And because of the diminishing returns of adding more and more and more and more insulation, adding an additional R10 to an already R45 roof, the energy savings aren't going to be. I wouldn't deem that to be cost effective. Added wall insulation. So you have to address 90% or more of the opaque wall. And in this case, the requirement is adding an additional R5 continuous. And similar to the one we were talking about before there, if you install half of that, if you did an extra R2.5, then you get half of the credit points that are shown there. And energy efficiency measure credits, improved fenestration. So it's saying area weighted U factor for all vertical fenestrations has to be less than or equal to a U factor of 0.22. 0.22, pretty dang sure you can't get that in a double pane window. So essentially they're saying installing triple pane windows will get you those points. Okay, and now, so again, we're not going to go through all of these. So we just want to focus on stuff related to the thermal shell. So renewable and load management credit requirements. So this is something new for 2024. And it's structured very similar to the way it is for the additional energy efficiency credits, in that you have number of points available by building occupancy group. And here's what that table looks like. And what this section is getting at is, if I look at those first 5 or 6 measures here: lighting load management, HVAC load management, automated shading, energy storage, cooling energy storage. What it's really getting at is, as we are strategically electrifying our grid here, and by strategically, I mean we're doing things like using air source heat pumps as opposed to electric resistance. And we're getting more EVs, electric vehicles on the grid, et cetera. We've got to be smart about how we're electrifying a grid so we don't crash the grid. And one of the means of doing that would be either to spend a lot of money in infrastructure and build out the grid more, or another avenue to take is work within the confines of the grid, but then do some smart things like manage the loads. So if we know we have a peak event, like, hey, yesterday, today, et cetera, we know late in the day AC units are going to be blazing. The utility would have the opportunity to reach out and say, hey, you know what? Yeah, if you could pre-cool your building today, lower the set point a couple degrees so that you could sort of ramp your AC back during the peak event later on in the day, so that your office building could float through that comfortably, but while reducing load at that time. That's what a lot of this is getting at. But there are some sections in here that do pertain to the thermal shell as well. And so I want to call those ones out. And so one is building thermal mass. And here they're talking about if you have a project where 80% or more of the floor area is unoccupied from 12 a.m. to 6 a.m. So again, unoccupied spaces overnight. There's some requirements about the pounds per square foot of thermal mass, and it can be located on a wall or on a floor. The HVAC system has to be able to economize, which means overnight that it can effectively, if it's a nice cool night, low humidity, that it can just, instead of running compressors to do the cooling, it can use outdoor air to do that. And again, those night flush controls. So like it looks to me like what they're saying is you can do some of this building thermal mass, get these points. So you're using the thermal mass to help you. I look at this as more as it's helping you in heating season, but then you have to be able to have the ability to control it during the cooling season so that you're not holding all this heat in your building. I think that's how this is kind of reading to me. And this last one is really interesting to me. Insulation embodied carbon. We're kind of going full circle here. We started the talk today talking about how reducing greenhouse gas emissions, we have to get after our buildings because that's the second largest contributor. So rather than just looking at the energy impacts of what are we using and and reducing the amount of energy we're using in the first place, getting at embodied carbon in building materials. And so there's one, granted, there's a small number of points, but at some points for the embodied carbon of in insulation products. And there's a couple pages within the new CBES that has all the information that you need to use to look at the material you're considering, to understand what the global warming potential intensity of that material is. And then there are credits that are determined by a formula that are back there in that back section of the code book. And an example of this is, so products, the typical products we see in our walls are as fluffy stuff. We'll see cellulose, which is great from a low embodied carbon perspective, fiberglass, which is actually on the lower end as well. We get into mineral wool, which is a great product for a number of reasons, but it's pretty high from a global warming potential standpoint. But there's a newer product here, at least in the US, Timber HP, which is a wood fiber based insulation, which is manufactured over in Maine, has very, very, very low global warming potential. And so that would be a material, a product that you could use in your buildings to get points for this. And so, because it couldn't be left well enough alone, there had to be a couple wrinkles in how these two sections work. So if your building were to achieve an additional 70% of energy efficiency credits, then you only need to get 50% of the renewable and load management credits. If your building achieved an additional 120% of the energy efficiency credits, then you don't have to get any renewable and load management credits. And we discussed that. And okay, we're almost okay. We're going to land on time actually with a couple of minutes to let you out early. So existing buildings, there is some new language around vertical fenestrations. It's just saying that it just calls out now that when replacing an old window with a new window, replacement fenestration shall meet those U factor table requirements. I was surprised that didn't exist previously, but it looked like that was new language, or maybe they just sort of changed the wording slightly. Again, language that I think we've all sort of known. If it's a historic building, make sure that you're consulting with the preservation office. And there's now an exception for an area weighted average of the U factor of replacement fenestration products, which is great. So if you've got different types of windows, and maybe some need to have lower STC ratings, et cetera, and it's harder to get a U factor that meets the prescriptive stuff, as long as your area weighted average U factor of all those replacement windows meets what's in that prescriptive table, you're good to go. All right, and with that, we've got 5 minutes left. I'm done getting through everything I wanted to say. I just want to highlight again that Efficiency Vermont is here as a energy code resource. We don't write the code, we don't enforce the code, but we do have people here that spend a lot of time poking around in it to help customers and partners and answer their questions. So please reach out to the Energy Code Assistance Center with questions.
Thank you, Steve. That was fantastic. Yeah, like Steve said, if you have any questions, feel free to put them in the chat. Also, you can use the raise hands feature in the toolbar on the bottom of your screen. You can raise your hand, and I can have you come off mute if you'd like to talk about any questions.
And if there are no questions, you just got 5 minutes of your life back.
Yeah. Mm-hmm. Not seen anything come in, but I believe there might be a small survey at the end of this call, so if you don't mind, it might take 1 to 2 minutes filling that out. Give us your thoughts. Let us know how the call went. Otherwise, it looks like you have now 4 minutes of your time back. So thank you all for attending, and Steve, thank you as well. And as always, if anyone has any questions, give us a call. Thank you. Bye bye.
Thank you all.